So I'm Jirka. And I'm going to be giving a talk. Full disclosure, Jake ambushed me last Friday. It was almost midnight, and he told me that only I can save this group by giving any talk because nobody else was willing to. So, because I was already tired and I did have something to drink, I kind of nodded at him and he understood it as an agreement. I did manage to throw something together. That being said, please be merciful because it's partly made of things that I've created before and I've kind of had to adjust it over the work week. So, you know, not everything is going to greatly fit together. Still, I hope you're going to enjoy it. In short, this talk is going to be about Keras, about machine learning, and about specifically that Keras library. What is it? How can you use it? How you shouldn't use it, maybe. What is in it, and what you should maybe consider it using it for if you ever want to try making your own neural net for anything. I'm not gonna be building GPT anything here because this laptop is, well, let's just say it doesn't make sense to try anything of the sort. I am gonna run some models I made in the past. I'm gonna introduce you to how to build very simple classifier which is so woefully outdated that you would get laughed at if you showed it to anyone else. Which brings me to my first question to you. Does anybody here use Keras or any other library for, you know, handling artificial neural nets? Anybody? Okay, awesome. So nobody's gonna notice the mistakes I'm going to make or the omissions I will introduce. Anyway, the point is, I'm in the clear. So first of all, what is Keras and why you should know something about it? So Keras library, it's spelled K-E-R-A-S, is a machine learning library, a front end essentially, which you can use to build your own neural net in a, shall we say, Lego-like fashion. So unlike other libraries in Python that you may know, you may have heard of at least, like PyTorch or TensorFlow or Tiano, all of these are obviously fine and awesome in their own way, scikit-learn also, but they all expose you to too much math, which is not always what you want when you want to just build something and prototype something that you just thought of. Often enough, you just need to have something that works and evaluate it relatively quickly. And Keras is great in this case because it introduces you to a very slick and simplified interface. The API is extremely simple to the point where you can virtually create a neural net without supplying any arguments to any of the functions, almost. Well, almost. There are a couple of arguments you may have to supply, but the point is that there is very little you have to actually write. It also has so many examples littered all over the internet and on their own website that you can, you know, just copy what someone else wrote and then slap your name on it and just say, yeah, I made this. I'm not saying you should. And also, it has lots of great integrated auxiliary functions. So, for example, you can download a lot of the well-used and well-known datasets like MNIST, which I'm going to be using in this presentation. You can optimize hyperparameters of your model. So you can basically just say, hey, Keras, I want a model that does this thing, whatever it is, very, very well. And I want it to have, yeah, sorry, go on. I will get to it. I'm trying to explain that exactly. So you can just say, hey Keras, I want a neural net that does this thing very, very well, and it has to have at most this number of layers, and it has to be at the most using this much, you know, parameters and such, and it just works. It just picks those hyperparameters, those things you set that are the boundaries sorts, and it just tries its best to figure out how to make it work. Okay, let's be honest, sometimes it doesn't, because you just picked something at random. But the point is that often enough it does, and if you know what you're doing at least a little bit, it can optimize the architecture for you in very little time. So that's just one of those auxiliary functions it has. It also has some ways to maintain data, to split it into sub-data sets, which then can be used to verify function of your model. I'm going to show that as well. Now, Keras is primarily work of François Chollet. I think I'm saying his name right. Maybe I'm not. He's French. The point is that he's the guy who kind of started this thing. Now it's an open source project, anyone can contribute. I have contributed. It's very easy. There are very friendly people there. He also published a book, Deep Learning in Python, which I have bought and which got me through my my last year in university. And I very much encourage you to try some of their examples they have on their website. Their website is keras.io, and I'm going to show it to you at the end of the presentation. Now, what am I going to present? I'm going to show you how you can make a very simple neural net in Keras. I'm going to show you how you can train it, how you can verify that it actually works, and how to interpret those things that are going to get split on the screen. I'm also going to show you a slightly more complex example, something I made for myself just for fun. I'm going to show you first few steps in training of that model. However, I'm not going to show it to you complete because this computer just can't handle it. It would take several hours maybe, and I'm not willing to sit here for several hours. Plus my battery is going to run out before then. Sorry? Yeah, you in the back.
How much beefy machine I need to run some basic stuff in Keras?
Basic stuff? For basic stuff you can have laptop from 2011. Okay. For more complex stuff, like, I don't know, what I have, what I've made and what I'm gonna partly present, the more difficult thing, you can do with consumer GPU for desktop from 2016. That's fine. If you're willing to wait a bit longer, you can go several years back. It's fine. It's just a matter of how much time you're willing to spend versus how much money you have. So that's kind of the good thing about it. The bad thing is that as you get more complicated setup, as the model grows in complexity, so to speak, you approach the point where training is kind of going to take several years. So, I mean, when the clock starts showing you numbers that are larger than the loss of the model in number of digits, that's the point where you know you need to buy better GPU. Okay? But the good news is that these days you can just sign up for a free account on Kaggle or for Google Colab, and they're going to assign you a virtual GPU which you can use for free, practically. I mean, you're going to be giving them your data, obviously, but I mean, like, other than that, it's for free. So, you know, you would be fool not to take it, right? And then there you can try lots of more complicated stuff. I've done that. I've signed a deal with the devil. You can do that too. Anyway, moving on to the actual presentation. In this case, I'm going to be running everything in a container. I'm going to use Podman as a runtime because I don't like Docker and because I'm from Red Hat. Now, I'm going to be using a pre-created image from, yes, Google, for their TensorFlow platform. I'm using that image because it's accessible. It's, once again, for free. I've also extended it in the past, but I'm not going to show that because that doesn't matter here. It allows you to easily hook up the runtime with your hardware, including your GPU. Now, full disclosure, I know the CPU version of this works on this laptop. I have no idea what the GPU version is going to do. And I'm not going to explain exactly what these arguments on the command line do because I don't have that much time. The point is that I'm just exposing a couple of port. I'm just exposing a port so I can access the web. Sorry. Something happened? I don't know. Okay. The point is I'm just gonna expose a port so I can access the web interface, and I'm gonna mount a directory over here on this machine of mine. So let's see what's gonna happen. Yeah, it's gonna spit out this thing. Now all I care about really is this. Now try not to pay attention to all these other tabs, those are work related, and I'm not gonna show them to you anyway, so I don't know why I even said that. So this is what's going to show itself to you when you start one of these images. It's a Jupyter Notebook runtime, obviously. If anybody ever worked in Jupyter, you well know what it's about. In our case, I only really care about one of those things here, which is imaginatively named Pyvo Demo Notebook, and also about this generating digits on demand notebook. So the Pyvo Demo is what I made for you, and generating digits on demand is something I made for myself slightly longer ago. I have verified that both of these do work, and we'll see if they work even now. So first of all, for those who don't know Jupyter, Jupyter is an example of something called literate programming, something Donald Knuth pushed a lot, and I think still pushes. The point is that you write code as you would write text, and comments are not separate from code; they are integral to the code. And ideally, you should write as much in a comment as you write in a code. That's why you have these text cells here, which are just filled with passive text explaining something that's happening. Now, you can of course read the text, but I think it's gonna be more fun if I'm just gonna explain it to you. So over here in this first cell, all I'm doing is importing a bunch of libraries. I'm importing TensorFlow, NumPy, OS, and Keras layers, and also time. I have no idea why I'm importing time. I think it may be some leftover for something else. I'm pretty sure that's not necessary. Actually, I'm very much sure it's not necessary. In principle, you could just do with Keras, layers, or Keras. Now you may be wondering why I'm not importing Keras directly. And that's because some time ago, TensorFlow just decided to throw down the gauntlet and just said, okay, we're gonna integrate Keras on top of our thing. So what TensorFlow does effectively is that internally, big portion of their modules, their offering, is basically just Keras imported from somewhere else. Now, I can import Keras just, by itself, but if I import it from TensorFlow, I may get the GPU to work, which would be nice, so I'm importing it from TensorFlow. As I said, Keras is a front end. You can order it to use any backend, so you can order it to use TensorFlow or Tieno or whatever Microsoft is peddling. The point is, it's kind of plug and play. In this case, the runtime, the backend runtime is set hard to TensorFlow. Also, one amusing thing, if you look here, you see I'm getting a log here. And if something goes wrong, you can see it here very explicitly. All the error logs and warnings and such are piped straight into the terminal. So if something doesn't work, I'm gonna look over there and you're gonna see very clearly what went wrong, what I messed up. So yeah, so this is just a normal warning message. TensorFlow spits this out whenever there's something missing or it doesn't understand something. Don't worry about it, it's happening a lot. Now in our case, we're gonna be using MNIST dataset. That's a very old dataset for handwritten digit recognition. Now that's an old problem. I think it started with post offices when they needed to decipher what people were writing on envelopes. The point is that this is a dataset from, I think it's National Institute of Science and Technology in America. They have created it a long time ago. Keras is serving it through very friendly API. You just do this little call here, keras.datasets.mnist.load data, and it's gonna curl all of it, all the images, straight to your machine. Now, obviously, you know what this means. This means there's plenty more datasets where this one came from, and it's all just as easy to get them. Now, fair bit of warning here. Some of those datasets are hefty. We're downloading images, in this case, a lot of them. The good news is they're very small. It's just 20 by 20, 28 by 28 by 1, you know, monochromatic. But some of them are fairly big compared to this one even, so make sure you have plenty of room on your hard drive. Okay? Like in this case, you can do with a very old laptop and it should be fine, but some of the bigger ones, I don't know. So what I'm doing afterwards is this call gives me a handful of, shall we say, data structures I can work with. Unless I supply any additional parameters, it's going to give me dataset split in 2 parts. This is very important. It's going to give me the training subdataset and the testing subdataset, both with their own labels and with the images. Why is that necessary? Well, first thing is neural nets tend to sometimes kind of, well, the exact term is overfitting. I prefer lying. Or to be more exact, when you train a neural network for long enough, you get to the point where it understands so well what you're feeding it that it's not learning anything new. And what it does is that it starts to optimize itself. Basically, it starts trying to make this as clear as possible. It's trying to fit the data to the point where it cannot really work with anything else. If you let it run for long enough, it's going to have trouble recognizing new things and actually classifying them or dealing with them appropriately. Now this is fun games when it's like, you know, digits, but this sort of behavior can be very embarrassing when you use it for something else, say for a face recognition. I've repeated this example numerous times in the past because it's very, very telling one. Google had kind of neural net a long time ago, a couple of years ago, which is a long time in this area, and they trained it on faces, and it was supposed to recognize whether or not a person is in a picture. What they didn't realize at the time they were training it is that they were giving it only a very small subset of possible faces on this planet. Namely, well, almost exclusively people from North America and Europe. And we may see a problem here already. When the net encountered something it didn't know, like say a couple of people, you know, I'm not saying African American because I'm not sure, maybe they were just African. The point is, when it saw black people for the first time, it didn't mark them as people. And I'm gonna give you, you can figure out for yourself how it marked them, but Google had to apologize very profusely, and that neural net was scrapped and retrained. And it was partly due to overfitting, because apparently the data, although deficient, contained actually some black people, but the avalanche of white and Asian faces was so strong and so heavy that the model just decided to, well, this is extremely unlikely scenario, you know, someone having a black face, so I'm just gonna, you know, discard those. I can't encounter them anymore. I'm humanizing the model in this case, you know. The neural net doesn't think like that, but the point is, it behaves as if it does. So splitting between trained images and test images allows you to verify afterwards if you have actually created a model that can generalize on new data, or if you have created basically just, you know, something that's pointless, that can just work with things it has already seen. And we're gonna split this dataset later into even smaller parts, so keep your eyes open for that. Now here's something else I'm going to do with these data structures. I'm going to reshape them into something else. Now, reshaping is one of those basic operations with tensors that you're going to do a lot, either directly or indirectly when it comes to neural nets. Basically, you're just taking data structure which has a bunch of numbers in it, and you're going to turn it into slightly higher or lower dimensional version of itself. In this case, the images are all flattened into one-dimensional array of float numbers. So basically, if I just, you know, opened one of these images straight away, what I would get is 28 times 28 floating point numbers. That's not an image, really, you know. I mean, it is an image, and technically, practically, however, you wouldn't recognize a digit in that. And neither would the model I'm gonna build. So what I'm gonna do is gonna reshape it back into the shape it was written in, which is 28 by 28 pixels. And I'm also putting this little number here. I didn't have to, technically, because the function could just figure it out, that it's supposed to have the one dimension very, very small. But I'm doing that just to be extra sure. This number 1 indicates that there's just one color channel in all of this. If I had more color channels, there would be 2, 3, 75, whatever. The point is, this way you can use this same function call, this same API, to work with multispectral images, and you can use it to work with, you know, whatever, you know, ranges of colors you have. And finally, this thing over here, I'm gonna cast it into float, 32-bit float. Once again, technically I could avoid that, but it's a safer way to handle this, because you never really know what this thing is gonna produce unless you read documentation, and nobody does that. So it's just better to err on the side of caution and cast it. Oh, and this final thing, I'm saying that I want the first dimension to be the same as the first dimension of the previous data structure. So basically what I'm saying is that you're gonna take this large data structure, which is the first dimension is number of the examples, and you're gonna turn it into something that is the same first dimension. But the second and third dimension is gonna be 28 by 28, so you need to kind of split it apart and reshape it. And finally, you're gonna keep the last dimension it has, okay? So in the end, we're gonna have 4-dimensional tensor, which seems odd, like we're gonna be just dealing with, you know, 2-dimensional images, right? But the third dimension here is the color, and the first dimension, the one I'm setting here, is the number of examples. The next thing I'm doing is I'm normalizing them. So the images are arriving in integer format. Technically they are floats, but in practice those are all integers, from 255 to 0, 8-bit numbers. Now, if I'm going to be feeding that to a neural network, it's not going to work exactly well. The thing is, neural nets mostly work with floating point numbers. They can adjust, but it's easier for them if you kind of make sure that the numbers are between 0 and 1 when they arrive at the input. There are alternative ways to do that. One of the alternative ways would be to have input basically already doing that once you feed it a raw image. You can do that. There's a special layer that can do that for you. But yeah, the gradients, otherwise, I don't want to get into technicalities because I don't have that much time for it. But the point is that most of the time it really likes floating point numbers, relatively low floating point numbers. Otherwise, the gradient descent algorithm tends to suffer. Anyway, this is basically just what I'm doing here. Normalizing it between -1 and 1, which works almost exactly as well as between 0 and 1. The gradients won't explode straight away, and it should be learning way faster. I'm just gonna quickly run this cell so you can see what's happening. And it's very fast. This is like, you know, just a bunch of numbers, right? And the splitting of the data set and normalization is exactly as fast as well. I'm gonna set some constants here. The first one is number of classes I want to detect. That's 10, obviously we got 10 digits. And the next thing here is I'm gonna reshape the label part of the data set. So there's a helper function for that in my case. Originally, the data set comes with labels defined thusly. Just let me show you. If I'm gonna put you the train labels here. So you can see it's got exactly the number that's written on the digit. If you can't read that, just tell me, okay? So it's 5, 0, 4, and so on. That's not really helpful for me. I want it to be easy on the neural net, and the neural net doesn't really do larger integers very well unless I force it into doing that for some reason, and I don't want to do that. So what I'm going to do is I'm going to do a categorical encoding of these. So what's going to happen is that for each one of these values, there's going to be new category created, binary encoded. So the neural net just has to produce 10 numbers at the end, showing probabilities of belonging into individual class. I can then wrap it into some helper object or method, and it can decode it back to normal human numbers. But this way, it's going to be way simpler to, train the network. And that's how fast it is. This is just deterministic algorithm. I'm just going to write the train labels again so you can see how it looks. Yeah, see? We get an array, and for each one of those images, for each one of those training examples, we get one of these arrays, just binary digits that signify to which class the image belongs. Of course, the first one here is signifying that it's 0, and this is going to be key to the training. I'm going to set a bunch of other variables. I'm not going to focus on them that much. I'm just going to say that in this case, I'm setting the size of the buffer into which the data set will be loaded, so it's easy, so it's quicker to get on the intake for the network. And I'm going to be setting the size of the batch. It's also an important parameter, yes. Larger batch sizes were one of those things that kind of helped propel deep learning forward, because it turns out that if you give a relatively large batch of examples to neural net for one step of the training, it helps it to get to that optimum faster. And I'm going to use Keras for the rest, but in this case I'm using TensorFlow. TensorFlow, it has wonderful functions for squishing data sets together and feeding them to neural nets. So I'm just going to use the training images and training labels. I could do without this, by the way. This is just a simpler way to demonstrate a thing later. I'm going to set the batch size, and I'm also going to shuffle it. So it's going to be different every single time I'm going to feed it to the model. Okay, yeah, we get some unknown error here. Oh, yeah, that was because I highlighted part of it, sorry. No problem there. Moving on, I'm just going to create a directory for the saved model, and I'm going to get to the interesting part. So, for building models, there are basically two ways to do it in Keras. The first one is a sequential API, which I'm demonstrating in this case, and the second one is the functional API. Now, the sequential API is for simple feed-forward models. One input, one output, nothing else. That's more than enough for us. We just want to classify some images, but for anything more complex, you need to use the functional API. I'm going to demonstrate functional API later though. Most of this you see here is just, some, not garbage per se, but it's helping me to do the thing I want. So here at the very top, I'm just checking if the model cloud already exists, if the model was already trained before, and if it does, I'm just loading the model, okay? Keras can save and load models, obviously. I mean, I don't even want to say this because it seems so obvious that, framework that's handling models from deep learning should be able to load models and save them, but it does. And if it's loaded, it just returns the loaded model. And over here we have the actual model definition. So, as I said, there are two ways to build a model. The sequential one I'm demonstrating here. You just give it a list of layers you want, it connects them, and returns the model for you. Now, I'm gonna just go through this very simply. I think most of these layers are self-obvious from the name, but I'm gonna maybe stay a bit longer at the convolutional ones. So the input layer is just input. It just means that it accepts whatever you feed into it, if it has the right shape. If it doesn't have the right shape, it fails and it screams. you can go around this issue. If you don't define any shape, you can actually have some pre-processing layers that handle it for you. So that thing I did at the beginning with the floating point numbers, the division and so on, you can have it here. And then you can deploy the model without any pre-processing because the pre-processing is baked in. In retrospect, I maybe should have showcased that instead, but I didn't because I kind of forgot about it. Sorry. The next layer, I'm going to stay a bit longer on this one, is the convolution layer. So back about 10 years ago, or even more actually, when the deep learning was finally getting started, they discovered that one of the ways you can process images is by using something called convolutions, or specifically learned convolutions. So instead of just training individual neurons, individual computational units, you can basically train them in larger, shall we say, subdivisions together. You can make sure that the spatial information is conserved and it's not lost. Because if you're training just individual neurons, well, the neurons don't know what's next to them. They just know that this is the input I'm getting, and they have no idea what their neighbor is getting. This is, in many cases, what we want, but when it comes to images, knowing what the next pixel to the right and to the left is kind of important, right? Because that's what makes the feature. Like, if you know just what the pixel in front of you is, you know the color, that's awesome, but completely useless. So, in this way, it was for the first time possible to actually treat larger and more complex images the same way we used to do simpler ones. Because now we could actually take the spatial information into consideration. The funny thing they discovered, the trained filters, the results, actually approximated things we knew from human psychology. About the first images people are able to recognize, babies, little babies. You know, crosses, wiggly lines, circles, and so on. Turns out the first layer, or the first filters, usually end up looking somewhat like this, recognizing borders, crosses, lines, and so on, which may seem like very good example of actually getting somewhere ahead, because up to that point there was very little idea of how to handle vision. Now we knew, from that point on, we knew that we were on the right path. So in this case, the layer is defined thusly. We know it's two-dimensional convolution because our image is two-dimensional. It can be also three-dimensional or one-dimensional convolution because your filter can be or one-dimensional temporal data. For example, it can be used on text tokens even, or sound. So you can use one-dimensional convolution in the same way. Or on four-dimensional data, you can use it on video. You can incorporate time dimension into it. But in the two-dimensional case, it's very much the same thing. I have asked for 32 learned filters with kernel size, that is the window. The size of the window I'm going to be considering is going to be 3 by 3. So for each 9 pixels, we're going to compute a new value for that filter. If you're thinking like, wait a minute, the output is going to be smaller than the input, you know, like in width and height, yeah, it's going to be. And that's the good point. Because that means we can effectively save memory. Because for every single, shall we say, for every single tensor, we have to allocate some memory either in RAM or in the GPU. And like in this case, it's 28 by 28 by 1. But imagine if you had some larger pictures with 3 colors or more, then it would get crazy very quickly, especially because you need to then multiply these matrices or tensors with each other later and with the weights that are defined. And weights are also basically tensors. So if it's smaller, it's actually better. And finally, I'm asking for ReLU activation, which is rectified linear unit. Now, activations are basically the functions that give any sort of interesting behavior to your neurons. I mean, it's non-linearity, essentially. To be perfectly straight, to fully explain this, it would take way longer than just 1 hour or even half an hour I have. So I'm just going to focus on the part that if you want neural nets to actually learn anything novel, you have to introduce nonlinear functions in there. It used to be that everybody used sinusoids or tangencies or whatever. Then they figured out, hey, all that matters is if this has derivation. You know, if you can derive it, if you can actually, you know, look at the slope of the function afterwards, then it's fine. We can use whatever. And it was like, yeah, okay, but how do you make that simpler? Well, we can define the derivation algorithmically. We can use computational algebra, computer algebra, to just say, hey, derivation of this function is actually this. And we can kind of approximate. So ReLU is actually just a linear function that at one point gets a slope. Slight different slope than it had before. Arbitrarily decided, basically. And it works, because we have defined special derivation for it. Now, no such function exists in practice, as in you have to kind of define it as a if-or thing, but you can define derivation for it manually in the same way, and then it just works. And it's also very cheap computationally. You don't really have to, you know, tax the computer that much, and you can make much larger model with it. Next one after that is max pooling layer. This is one of those layers that even further condenses the features. Basically, it looks for the maximum output in a given area. In my case, it's 2 by 2, and leaves that, and everything else it discards. I'm feeding the result further into another convolution layer, this time with 64 filters. I can afford more filters at this point, because the output of the max pooling layer is already smaller than the input was at first. And then again to max pooling. And finally, what I'm doing is I'm taking the filtered image, which at this point is like, I don't know, a couple of pixels by a couple of pixels with 60 times 64. You know, for each filter there's a, you know, one more layer of that. And I'm saying, you know, flatten it. Turn it into one-dimensional array. You know, turn it into one-dimensional tensor. And then I'm gonna say, okay, now with probability of 0.5, drop each value. So for each value in that one-dimensional tensor, there's a 0.5 probability that it's gonna equal 0 when it gets to the output. It may seem strange, but this actually helps the model generalize. Because for each iteration, the model can lose some weights in this final layer. It can lose some neurons, actually, seemingly. So it has to be more robust. It can't just rely on having all of these parameters. It's going to lose half of them every single training iteration, so it needs to make sure that all of them are general enough. And finally, I'm feeding that to one last dense layer. Now, dense layers are where neural nets all began. They are just individual neurons connected to each of the previous neurons in the network. Now, I'm gonna just have 10 of these, because one is for each of the digits we have, and I'm gonna use something called softmax activation. Softmax activation is basically just making sure that the sum of outputs is equal to 1. This means that ideally, hypothetically, ideally we want to have just one of the output neurons to have value of 1, and every other to have value of 0. And this is gonna kind of help with that very much. Now, I'm just going to go ahead. I'm giving this as a list of layers, and then I'm gonna build the model. I'm also going to print a summary of the model with the sizes of the individual layers and their description. And finally, I'm going to compile the model. Now, the model compilation requires a couple of arguments. First, it needs a loss. It's a function that defines how far is the model from the desired output. So, in my case, it's categorical cross entropy, which means I'm going to take those one-dimensional arrays. At the beginning, I created with a categorical encoding. I'm going to compare them with the result. I'm going to use cross entropy to get how far they are. I could use other metrics, by the way, but categorical cross entropy works very, very well. It gives a smooth surface, and that's better for the gradient descent we're going to be using. I'm going to use Adam Optimizer. That's an algorithm that basically builds upon the older gradient descent technologies and makes them computationally feasible on smaller machines. Oh, sorry, I just realized, I don't know, how many of you know what gradient descent is? Cool. So, I don't have to, I'm sorry, I will. So, like, imagine if you will, landscape, you know, hills, valleys, plateaus, and so on. Now, that's how you can view performance of your model, okay? So the hills are the cases where the model isn't doing exactly well, you know? The higher it is, the worse it is. The further it is from the ground, from where you want it. You want it to be as low as possible. You want it to reach the lowest point on the landscape. Problem is, you have no idea where that lowest point is. And it can be anywhere, really. And for each model, it's different landscape. So, what can you do is you can treat the model, or to be more precise, any sort of function, not just a neural net, but it can be any sort of function you can learn, you can teach this way. You can treat it as if it was a small pebble, you know, a small stone, or a marble, you know, and you can push it a bit in a random direction. Now, if you push it, it's going to fall down a hill or a plateau, most probably. It's going to reach a lower point on that landscape. This is a very old optimization technique. It basically relies on facts of physics we know from our daily lives. You may be wondering, okay, but how do I know I pushed it in the right direction? And that's where those derivations come in. Because from derivation you can find out what? Okay, how many of you had calculus? I'm kind of hoping that at least somebody raises their hand. Cool. Okay, so from derivation you get slope. Derivation is a slope, basically, in this case. So those derivations can tell you where do you want to go, in which direction do you want to push the marble. And Adam Optimizer and the family of optimizers derived from Adam makes this actually computationally feasible, because otherwise you would have to run a very complex simulation of Newtonian physics, because for each one of those parameters that our neural network has, and those are tens of thousands in this case, which is very simple, you would have to really compute, you know, the slope, and then you would have to figure it out and all. There's actually a lot of nice visualizations of gradient descent. If you look it up, you can see how the marble, so to speak, moves on the landscape and drops down the hill into the rice alley. Also, please note that there can be more than one valley. There can be many more places where the marble can go. Some of them can be higher than you would believe, and that's why we need the test subset of the data, so we can verify how high it actually is. There's something called local minimums, and we want to avoid those. We want ideally the global one, which we don't know where it is. And there can be also more than one, which is unfortunate, but well, we'll get to that. And I want one additional thing. I want a metric. Now, unfortunate thing about the neural net loss function I've been talking about previously, the thing that says how high it is on the landscape, it can be counterintuitive. The values, I mean, we all know that they are supposed to be lower, and that is better, but that's about it. It helps to have some additional metrics which you can present to people and to yourself. In our case, it's going to be accuracy. Basically, the percentage of cases when our model was right. And after we have defined our model and compiled it, we can start training it. We can call a fit method on it, which are input images, their labels, the size of the batch, which we have defined above, you know, the 128, and number of epochs. An epoch is a sort of a series of training steps. After end of each epoch, the dataset is shuffled and it's fed again in the next epoch. Depending on the way you have defined your model, there can also be a checkpoint called, there can be a number of other things happening, you name it. The point is, the epoch kind of divides the training into individual stages, which you can then variously treat. And I'm going to ask for validation split. I'm going to say, hey, I'm 10% of all of those images I just gave you for training, keep them aside, and at the end of each epoch, test model on those and print out the results. Now, it's not going to be training on those images. It's just going to be tested on them. You may be asking, okay, why am I wasting 10% of all images just to do something I'm going to do at the end? Well, as I said, the thing about callbacks, this way you can see how the model would be performing on novel data before you finish the training. Which also means you can stop the training halfway through when it's not getting any better. But you may be saying, okay, well, if you got that, if you're already doing that, then why do we have the test subset? Well, the thing is, although the model didn't actually train on these images, on that 10% I'm setting aside here, it kind of knows a bit about them. It does so indirectly, because for each stage, for each epoch where it was allowed to pass this sort of test, it was doing well enough. This is called informational leak. It's happening whenever you train these networks. Some sort of information from the validation dataset is getting in there. It's not as much as from the training dataset, but it is there. So you need to be very careful about that. If you're repeating your experiment, try to split the data in the same way. So for example, you don't by accident end up in a situation where that model you're training is doing better, but only because it received the nice subset. It can happen. It did happen to me. And finally, we're asking for evaluation. We're giving the model our test subdata set, and we're saying, please shut up. We have heard about it enough from you. And finally, we're saving the model and printing out some statistics. Before we start, I just need to check one thing. I need to know whether or not I've already saved the model. It should be called digitclassifier.h5. That's a format of models. I'm just going to look it up real quick. So it should be in notebooks, models. No. Oh yeah. One more layer. Yeah, train models. Right. Sorry. Yeah, there it is. So we need to get rid of this one because otherwise I wouldn't be showing you anything. Okay.
While there's a break, could you turn off the night light in GNOME?
Sorry?
Could you turn off the night light in GNOME?
Oh, yeah. Sorry. Yeah. Okay, so now you can see everything, right? And note that I've wrapped this into a function which I can call. Okay, and now I'm gonna first train, and then I'm gonna get summary.trained model. So, training has begun, and here's the result of our summary operation. So, by the way, training is going on here, down over here. You can see each step calculates new loss and accuracy. And over here, we get validation accuracy, which is already extremely high. After just one epoch, we get accuracy of 98%, which is still rising. But I want to focus on something else. Over here, you see number of parameters. That's the number of numbers we're giving our algorithm to optimize. In total, it's just a bit over 34,000, which is extremely small. That being said, it would still be very much difficult to do this sort of thing only a couple of decades ago. Note that the flatten and dropout operations, the flatten and dropout layers, have nothing to optimize. They're just dumb operations. They're just deterministic. which is good because they're cheap, and so do the max pooling layers. And the training continues, and our validation accuracy has reached the point where if I had actually defined a callback, it would be stopped. The training would stop at this point. But I'm still letting it continue just so we can see what's happening. You see that the normal loss, has been dropping for a while, and it still is dropping a bit. So we're now entering the area of, shall we say, overfitting. Our model is learning, but it's learning only things we have already shown it. And at this point it's trying to, figure out how to learn it even better, which means that if we show it hypothetically something it hasn't seen before afterwards, it might break. In this case, since we're just dealing with digits, it doesn't really matter as much. Plus, we're seeing that the validation accuracy is still rising. We are now at 99% accuracy, over 99%. But it's fluctuating, you see, it's not rising nearly as much as it used to. I'm going to let the training finish, and then we're going to see the final results for this. And afterwards, I actually can start already. I've said that this is an example of sequential definition of the model, the simple one. By linking together layers as if they were functions, and then saying, okay, and turn this thing into a model. This means you can create much more complex things. You can create models with multiple inputs, multiple outputs. You can create models that work in tandem together. I'm going to show you one of those later. And you can actually create things that are impressive even today, and not just 15 years ago. It would be. So we're just finishing the training, and finally we got it. So our accuracy, our final accuracy, is over 99%, and we have ended up with a model that would be groundbreaking around my youth, and with just 35,000 parameters. So we can train this on the CPU. And I'm just going to show you how the logs look for over here. I think there should be some sort of screens about how it can find the GPU. Yeah. Okay, nothing terrifying. Okay, yeah. So over here, you see the CUDA driver. It's trying to look up the GPU with CUDA capability, and it just can't. So that's why it's so slow. Like if I was doing this on my PC, it would be done like a minute ago or 2 minutes ago. I'm going to show you the functional API though. First, we need an input layer. We've already talked about it, it's the dumb thing. I'm going to call it imp, and it's just going to be Keras, or more likely even just layers, because I imported the layers. And I'm going to call it input. I'm going to be putting input shape, what we talked about, which is going to be 28, and 1. I'm just going to check real quick if this is the way I've done the buff. I don't want to get embarrassed. Yeah, it's exactly that. And so that's our first layer. Our second layer, and I'm going to make a simpler model in this case, is just going to be the two-dimensional convolution. I'm going to call it X. Once again, it's going to be layers. Yeah, it's convolutional 2D. See, you have the 2D and 3D convolutional as well. And I'm going to ask for 32, and I'm going to get the kernel size 32. That's 32 filters. Kernel size is going to be 3 by 3. You can also make a symmetrical kernel. Okay, so you can like.
Even or number?
It can be. I think you can do also even, but the problem is that you then have to make sure that the layers kind of fit together. It's like little Lego pieces, Like if you have a Lego piece that doesn't fit on top of the other one, it's gonna kind of be unstable. In this case, it's just gonna fail on compilation. So the input shapes, the thing and the output shapes, the thing here you see, the output shape needs to be compatible with the expected input shape of the following layer. And you can see that the output shapes keep dropping the further we go down. So what you can do, if you don't count this right, it's not a complex math, but you should still think about it a bit, is that you can end up in a situation where there is nothing to work with for the follow-up layer. When it's like 1 times something, and then it just can't do two-dimensional convolution on that because the window is larger than the input, okay? So like, you see how we started with 28 by 28, here we're closing 2 pixels on each side for each dimension, and gaining 32 filters. And here we lose half of all those dimensions, which means we even further decrease the amount of data we have to process. And here we lose another and another. You know, it's actually the deeper you go, the less you have from what you have started with, but you have more dense information, the better representation of the input, at least in theory. In practice, if you do it wrong, you can also end up with worse representation of the input than you started with. There's actually a way to do that, to force the model to do that. I'm just going to do real quick. So in the functional API, you feed the previous layer thusly, just as if you were calling a function. You have created an object of the class conf2d, and now we're calling it with a previous layer we have created, and we can reuse that variable. And it was 2 by 2, right? Was it? No, I don't think it was. 2 by 2. And once again, we're gonna use the x, and because I'm lazy, I'm just gonna go ahead and just call it flatten. And flatten doesn't need anything as an argument because it's a dumb operation that just flattens the things in 1 dimension. And then I'm gonna use the dropout. And I'm just gonna give it a 1 parameter, which is 0.5. And once again, I'm giving it the previous layer. And finally, I'm gonna have a dense layer with 10 individual neurons. Activation is gonna be softmax. And did we do anything else here? I don't think we did. I think that was it. Yeah, that was it. And once again, I'm going to do the previous layer. Finally, I'm going to have our functional model, which is going to be Keras model. This time we're making the real one. And inputs, it's going to be in. Yeah, what happens from time to time is that you forget that you need to give the inputs at the end, and you actually name this x, and then you refill that variable with something else, which means that then you have to start over and just, you know, do it, redefine it as something else so you can keep it afterwards. It's an embarrassing sort of mistake that you don't want to show it, you know, publicly, much less on record. And outputs, which is going to be x. And we wanted to have, what would we do with it? We wanted to have the, categorical cross entropy, and with optimizer, with NM optimizer. And so this should be it. And, and I just forgot about input. What did I do with the input wrong? Oh, yeah. What's a wrong thing? What did I do here? Oh yeah, shape, not input shape. Yeah. So yeah, don't also forget about the name of the arguments. So, okay, so the model is done, but it's not compiled yet. Next we do the compilation thing. Compile, loss, categorical cross entropy, optimizer It's going to be Adam, and metrics is going to be accuracy. There's also a bunch of other metrics you can use. Okay, it's not just one. You can define your own metrics. Basically, anything, any function that accepts the expected output and the real output and returns some sort of number can be a metric. You can define one yourself. And that should be it. Yeah, we have compiled the model. We can call the summary. And yeah, func model. Something went wrong here. Something went very, very wrong here.
Oh, it's a live demo after all.
Sorry?
It's a live demo after all. Nothing was wrong.
Yeah, it is. Okay, you know what? I'm just gonna go put training straight ahead. Maybe it will work. Who knows? And I'm very lazy at this point. So what I'm gonna do is that I'm just gonna take this thing over here, this function call, and adjust a couple of parameters so we can see if it trains correctly. Yeah. So it's gonna be train images. I think train labels, and I think that's it. We'll see. Now this should be showing some output, but it's not. That's wrong. That's very wrong at this point. Tell you what, I'm just gonna rerun this thing and see if something else happens, because I'm not seeing things happening, and that's wrong. I should be seeing things happening. Okay, it's fine. So that's wrong. Yeah. Okay. Yeah. Finally, we get somewhere. Okay. So the batch size isn't defined. I'm gonna set it over at 64. I'm gonna say 5 epochs. Now it should be actually good. Okay. So it's right. Okay. So now we've made our first model with functional API. And you can see it's not doing as well as the previous one. But even though it's not as smart, you can see it has more parameters actually. It's because we haven't actually decreased dimensionality as much as we should have. So the last dense layer is getting much larger number of inputs than it had in the previous case. And it's not that the model is much smarter. Not at all, in fact. You can see the validation accuracy hanging just around the 97%, whereas in this case, in a previous case, when we were at the 5th epoch, and now we can see it because I get rid of it. Okay, that's bad. Anyway, so yeah, it's not as smart, but it's bigger, and it's one of those things that can happen with neural nets. Just please, if you remember how the training went previously, know we were at 99%. Okay, so please act as you remember. So yeah, so even a bigger model doesn't have to be as good as a smaller one, which is one of those things that neural nets can be a bit counterintuitive in. If you design a neural net in the wrong way, it's going to be large, expensive to learn, train, and completely worthless. And I'm going to show you another example, something more complex one, something that may put on itself. It's called the generating digits on demand. It's a thing I put on Kaggle some time ago. If you don't know Kaggle, it's a place where you can basically compete in the machine learning competitions, post your things, whatever you like. You know, it's kind of like social network for neural net nerds. And in this case, I made something for myself. In this case, it's basically a generative adversarial model, which, if you don't know what it means that you take two models, put them against each other, and say fight. And you want obviously one of them to win. Depending on what you want exactly, you want either the discriminator or the generator to win. Now the discriminator isn't a bad guy. He just wants to figure out which image is fake or which sample is fake and which is real. The generator isn't a bad guy either. It just generates things. from some noise, and it's trying to make them look as much as whatever, you know, you're asking for it. Now these two models work against each other, and provided that you've designed this correctly, they will be mostly in balance, and over time both of them will be getting better. And eventually you'll reach a point where none of them can learn much more. The discriminator is getting defeated almost sometimes, and the generator is mostly slipping away. And the result should be something that looks very much like what you fed to it in the beginning, but it's completely novel. I mean, nobody has seen it before. They have seen something similar to it, but not exactly this. If this sounds kind of like familiar to you, it's basically the same approach, but in much larger scale that the generative image models are using today. Things like stable diffusion and such. I mean, like, obviously theirs is much better than mine, but mine can print digits, so theirs counts. So, oh, well, it can actually, so yeah, never mind that. The point is that this thing can actually run on my PC, and I can train it on my PC. I can't do that with Stable Diffusion or DALL-E. And there's just a bunch of helper functions at the beginning. I'm installing some extra libraries here, you know, for image I/O. I'm preparing the dataset, the same one I prepared at the beginning of the previous notebook. I'm just gonna go through these very quickly. You notice these things are very suspiciously similar. Almost as if someone took part of this thing a couple of hours ago, deleted some stuff and rewrote part of it, and then, you know, renamed the notebook. Yeah, exactly. Anyway, like at the beginning, I'm making the generator model. I'm using the functional API here, and the generator model just takes, in my case, some sort of noise, and it takes something else also. It takes a digit. It has two inputs: the random noise from which it generates the image, and the digit which signifies what kind of output it actually has. So this is a conditional generative adversarial model. And finally, it, from this noise, makes some sort of output which should look like a digit. The larger noise, the more noise, the better, in a way, in this case at least. And you can see that the model is fairly large. It's 2.5 million parameters. So, like, on this PC, it's not going to work very well. I'm going to sample an input and generate image initially from this model without any training. And you can see it's not looking like anything. It's just the noise. A slightly filtered noise, but the filters are also randomly initiated, so it doesn't matter. Moving on, I'm making the discriminator. This one is sequential. It doesn't have to be as smart. So that's great. Made it. And I'm going to ask it to discriminate right away. And it points out, okay, this is very improbable to be, well, I don't know really, because it also is randomly initialized. It doesn't learn anything. So this is pointless. And finally, I'm making a classifier, which you may have seen before. The classifier, all it does, it just takes the image the generator produced, and it tries to figure out what kind of digit it should be. Now, what I'm using the classifier for is that I'm actually using it as a special kind of loss metric, for a special kind of loss metric. Now, normally, those two models would only care about how much are they able to cheat each other. But what I'm making them is, what I'm adding in is, I want them to not just generate something that is digit. I want them to generate a specific digit, which I just asked for. So if my classifier checks this output and sees it as a different digit than I asked for, then that's a problem. I don't want it. I'm going to be as close as possible to the output I want. So I'm expanding the definition of the loss slightly. So the discriminator loss and the generator loss are already fairly clear. And finally, I'm going to initialize those optimizers. You can specify optimizers as either an object or as a string, by the way. And finally, I'm making the digit loss, which is just a simple cross entropy. Note that it's not very smart. I'm not really asking for like a distance from the, the digit, because technically speaking, these are images. I don't really care. If I ask for 4 and you give me 5, it's still as wrong as if you give me 3, you know? The shape is just completely off. The fact that they're fairly close on the number line doesn't matter to me. So it's a problem either way. And I'm gonna compile that loss over here. Yeah. See? And I'm gonna initialize the checkpoint. So I save every couple of epochs. This is just a helper function, and finally I'm defining the training loop. This is the first batch of images I'm generating, which is fairly, you know, random. Obviously, those are not digits. And the training function, I'm skipping a lot. Sorry, I already overshot by how much? Half an hour.
Yeah.
Okay. And I'm gonna train, and now you'll see why it's important to have like something reasonable. So it's already doing something. I can hear the fan, but the problem is that it's desperately trying to do something on a CPU that GPU was meant to do. CPUs unfortunately aren't very good in massively parallel operations like matrix multiplications of this sort, so I would have to probably wait until my battery gave out, and then I would just leave.
So what would be the output?
Yeah, I'm going to show you how the output actually looks. I'm going to stop this, and I'm going to look up the, just let me, it's generating digits on demand, right? So I'm going to look for a good one, Kaggle. I'm going to show you how it looked properly. Okay, page. So this is Kaggle, by the way. A lot of people are posting their own models there. Sometimes even I do, when I feel bored and maybe a bit brave. And I'm gonna try to look it up. Yeah, there it is. 5 months ago. Yeah, that's me. Okay. So the output should be something like this. That's what I've had before. That's fine. That's fine. You can see that it's basically the same thing I've been showing you, just finished. And it's the training. Oh yes, 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 yes. And finally, here, we're getting the output of the final training epoch. And here, I have this nice GIF. Example of how it looked throughout the training. So again, I'm gonna make it a bit larger, sorry. So for each of those checkpoints, I've recorded what kind of digits it generated. And okay, and here it and save the output. So you can see how it progressed over time. This is, see? So to start, it's still not getting them right, but it's kind of there. 9 is almost fine, 3 is kind of, but yeah. So it finally gets, almost immediately, it actually gets to the point where most of the digits are recognizable. And after that, it kind of refuses them, but for most part, you can still recognize the 5, the 6, the 7, the 8, the 9. The 4 is a bit skewed, but it's fine. Notice that in the first few images of this GIF, you see kind of like a blob, just general, like, you know, like if you asked someone to just split, you know, color something, but it gets better. So that's the end result, the end output. It's almost recognizable as digit in every single case. Now if you want it to be fancy, you can parameterize the style of the digit, so slope, the skew, the size, the, you know, defects even, because all of these things are encoded somewhere in that model. You just have to get it out. So yeah, that's the end result. That I would show you that if I had a proper PC here and not a laptop. Any questions?
Any questions?
Or to be honest, any questions I can answer.
Why is 4 so bad?
Sorry.
Why is 4 so bad?
Yeah, I have no idea honestly.
Because it's so random.
No, I'm gonna be honest here. The funny thing is that when I trained it once before, it was better, and then it was worse. Now what I'm thinking is that for some reason, it picks up the style of the digit completely, well, because I'm not asking for a specific style, it picks them up randomly. So maybe there was a group of people that wrote 4 very badly, I don't know. Or maybe I'm just overfitting it. That's one of the possibilities. But yeah, the 4 is weird. Like, it's one of those things that I think, you can see it's kind of like trying to make it into 8 a bit here, see? Like, is it, maybe could I make it an 8? No, you can't make an 8. But I like it's trying, you know, it's almost there, for the most part, it's almost there, but yeah.
Maybe it's because the top of the number 4 is the only one that is empty. And for the algorithm it's basically enough to have just part of it to recognize it as a 4.
Yeah, I mean, it could be. The fact is that this is very naive implementation of the conditional generative adversarial network. So, like, it's possible I overlooked something. It maybe is that if I define the loss in a different way, it would be better. Yeah, I have no idea. I'm just guessing. Sorry?
These numbers are each time oriented in this order, I mean.
Yeah, that's the point. I wanted them on demand, so they're ordered 0, 1, 2, and so on.
Yes, and there are no rotations or some orientation, I mean.
You could ask for that if you looked into the parameters, and you can actually, there's something called latent space, and you can actually make sure that they look in a specific way. There's even a specific kind of models that are made just for this sort of thing. Those are called autoencoders or variational autoencoders, which you can use to extract any kind of style from, you know, anything, and then just kind of, you know, use knobs and such, sort of, in a software way, to like make it look in a specific way. There's a bunch of examples, actually, also with digits like this, I think, and with other similar toy data sets. So you can actually have them tilted and such. In this case, it just averaged out all the styles in the data set and just picked whatever was most common, you know. But I guess if you modify this setup, you could do this. Anyone else? Any? Okay.
If I have an object and I want to decide more things about it, like first category, is it green, yellow, or blue? Second category, is it big or small? And third, do I like it or not? Is it in general better to train more models, or to have one model with more outputs, or more complex output?
That's a good question. So, like, normally, it's a question of how much time do you have, and I mean, like a computer time, and for how long do you want to use that model. So, like, if it's something that's one shot and basically you're gonna forget about it after a couple of days, yeah, it's maybe better to just train a couple of smaller models. It's gonna be easier for you and it's gonna cost less money. If you want to use something for the long run, I would recommend going more complex. I mean, from the perspective of the model, it's just a question of adding a couple of more layers at the end as different outputs, or increasing the size of the output layer slightly. What you do with that output, how you interpret that, that's a wrapper thing around it. It's actually the easiest part in some ways, but it's like the key part. And if you want to do like a style transfer, which sounds like, I mean, like in your case, it sounds a bit about color and such. It's like a detection or about generation. What's the thing you want? Detection. So, I mean, like, yeah, so those are two different things. Detection is way easier than generation, because that's like, it just, you don't even ask about where something is, you're just asking about what that something is in the picture. So that would be fairly easy. You would have to find an encoding for all those aspects. So, you know, have red as 1 or whatever, you know. But you could do that. It's not hard. It's just a question of finding an encoding and then having the data set. So, like, you have to have someone or some people who are willing to go through a bunch of images and label them and say, oh, this thing is a red car, this is, you know, whatever. And that's arguably the most expensive part. The GPUs, compared to the labeling, the GPUs are cheap. So yeah, you can do that definitely. And the good news is that if you do it well, you can actually reuse something that you have made before and someone else has made before. Because those first few layers, as I was talking about the patterns, it recognizes, the crosses and such, those are universal. You can just cut off the first part of the model, reuse it on top of some other model. That's the most commonly done thing these days. Foundational models have made it so cheap that you can now just take someone else's work and get credit for it, which is great. And you can say that it's industry standard. You know, you're not doing anything bad. You're doing something that everybody else is doing. So, any last question?
Please, can you share the...
Just one. No.
This is not a question, but can you share your Jupyter book, or how to say it?
Notebook. Yeah, I can. I will. Do we have a place on Pyvo we could put it in, maybe?
We can put it in the Discord server and even into the notes on the website.
Okay, so...
It can be shared also on this description for today's meeting.
Yeah, we can edit.
Like, if you want to look at this specific thing I wrote, there's this site called kaggle.com I'm on right now, and you can just look up generating digits on demand, and that's it. Yeah.
Thank you for the questions. More questions afterwards, if they can catch you.
Yeah, I already... my throat hurts, sorry.
So, thank you, Jiří. Now, we'll get